Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So now today we will start the module 5. Okay, so in this video we will see structural and loading discontinuities for open section view. Same thing we had seen for the closed section view, now open section view. So our lecture topic will be first general aspects, then shear stress distribution at an open section view, and then idealization of a panel. So these things we will see in this videos. Okay, so now first is general aspects. So far we have been concerned with relatively uncomplicated structure. So what we have found on like in aerospace structure that we have seen, that was not complicated structure, right? And in what we deal with in for module 1, module 2, right, those was not the complicated one. That was a simple structure was there you found by the energy method, by the stress method, stresses that Hooke's law and all. So that was for the normal structure. Now, if complicated structure is there, then how to solve, right? So that is there here. So section which in practice would be formed from thin plate or by extrusion process, right? In that case, what we will do, if that plate is thin by extrusion process, if it's a form, then how to find that one? Okay. While these sections exist as a structural member in their own right. So just here, these sections exist in structural members, means in that many members will be there in their own right. They are frequently used, with those structural member, that is just for support of that one, frequently used to stiffen more complex structures. So now just see in this figure. So these are the members which provide a stiffness to this surface, that is the skin of this one. Okay, so that complex structural shapes such as fuselage, wings and tail surfaces. Thus a 2-spar wing section could take the form shown in figure here, right? So here, 2-spar wing is there. Okay. So figure 1, in which Z section stringers are used to stiffen the skin. So this Z section are used to stiffen this skin. So all these Z section are the stringer which provides support to the skin and stiffen to the skin. Okay. The thin skin, while angle section forms the spar flanges. So these are the angle section, right? Here. This is the angle section. This is the angle section, that is the spar. So this is again angle section. So these are the spars which supports the skin. Okay. Clearly, the analysis of a section of this type would be complicated. Now, for this separately you have to find first stringers, then a spar, then how much stress carried by the skin and all. So that becomes difficult, right? So section of this type would be complicated and tedious unless some simplifying assumptions are made. So solving directly is a tedious process. So how to solve? So means what we will do? We will go for some simplifying assumptions. We will make some assumptions so that we can simplify this one. Okay. So after making some assumptions, okay, we can simplify this and then we can solve. But that assumptions should not affect the accuracy that much. Means okay, just near to the actual one that should be there. Okay, so generally the number and nature of these simplifying assumptions, what we will apply the assumptions that should be what determine the accuracy and degree of complexity, means how much it's a complex and how much accuracy we require. The more complex the analysis, the greater the accuracy obtained. So if suppose more complex is there, like this one is there, right? Now, if you will measure like this, the total distance is how much? This from here to here, what is the total distance? If suppose you wanna measure. So first step, what you will do, just go exactly along this line, right? Exactly along this line, then you will get the more precise one. But in second case, just from here to here measure. Okay, this is the simpler, right? Then also, but that is not accurate. Go like this. Okay, from here to here measure, then from here to here and here to here measure. So in this case, in third case, also it's not that much accurate, but that will be more accurate than this one, but less from this one. So in this case, this will be the more accurate than this one, and this will be the least. So means as much as complex analysis we will do, that much more accurate we will get the result. Okay, so what we have to do is we have to just take some assumptions so that we can simplify certain level, not all the level. Otherwise, what happen? Our accuracy will get affected. Okay, the degree of simplification introduced is governed by the particular situation surrounding the problem. So how that, what are the surroundings are there, how those things will affect. So according to that only we can simplify that one. Okay, for a preliminary investigation, speed and simplicity are often of greater importance. So first, in primary investigation, what we can see that speed and simplicity, so that data structure should be simple, speed should not get affected, are often of greater importance. So in case of primary investigation, these two are having the greater importance than extreme accuracy. So in first preliminary, we are not bothered about the extreme accuracy. Accuracy is required, but not extreme accuracy. But in secondary level, what we have to must exact as circumstances allow. So as much as we can approach to the maximum allowable one, right? Or extreme accuracy with those surroundings. Okay, that way. So on the other hand, a final solution must be as exact as circumstances allow. So whatever the circumstances are there, in that as much as exact as possible, up to that we have to find. Okay, complex structural section may be idealized into simpler mechanical models. So mechanical model is just whatever the things are there. So miss whatever the structural section are there, we can idealize. Idealize is what? Nearly it's impossible, but still we are just assuming like ideal gas is there. Achieving ideal gas is impossible, but near to, we are comparing that with the ideal gas to the real gas. How much closer to that one is there? As much as that is the closer, that much their behavior will be good. So same way here, as much as the idealized, then one will be there that we can use, from which we have under given loading condition in the same or very near, just here, in the same or very nearly the same way as the actual structure. So either in the same structure as we can, or just very near to that original structure, we can do that one and then we can calculate. We shall see, however, that different model of the same structure are required to simulate actual behavior under different sim. So if different model is there of the same structure, but different model is different after changing the assumptions. Okay, that means with different assumptions of the same structure, if we will find that simulate the actual behavior under different system of loading. So it means that different behavior also will be different in different loading system. Okay, so now here we'll see what distress shear stress distribution at an open section B. Okay, so in the wing section of figure 1, stringers and spar flanges have a small cross section dimension compared with the complete section. So we are seeing here in figure 1. So these are a small size compared to this whole bigger one, right? So in this we will do some assumptions. Why? Because small stringers and spars are there. What assumptions? So just here, the stringers and spar flanges have a small cross-sectional dimensions compared with the complete section. If you will complete this whole section, whatever the stringer and spar was there, have the very small cross-section. Therefore, the variation in stress over the cross-section of a stringer due to, say, bending of the wing would be small. So, this one. Okay, the variation in this stringer or spar of that cross-section, because this is very small, that will be also very small. Okay. Furthermore, the differences between the distances of the stringer, centroid, and the adjacent skin from the wing section axis is also small. So now just see here that is there, right? So somewhere here, their center of gravity will be there. So from center of gravity to this skin, that centroid of this jet, right, to this skin is also very small. Why? Because we assume this is as very small, and center of centroid is here. Right. So now over this something will be there. Means definitely this distance also will be very small. Okay. Furthermore, the differences between the distance of the stringer, centroid, and the adjacent skin from the wing section axis is small. Okay. It would be reasonable to assume, therefore, that the direct stress is constant over the stringer cross section. So that's why over the cross section of this stringers and spars are just considered as constant. So it's not varying with compared to the overall structure. Okay. we could therefore replace the stringer and spar flanges, because now that is not even direct shear stress is also not affecting that much. It's just constant. So we would therefore replace the stringer and spar flanges by concentration of area. Now, whatever the concentration of area is there, right? This much bigger size. Now, the whole area we will concentrate to here. Just like any mass is there, anywhere mass is acting. What we are saying, this mass is concentrated at the center of gravity, or just like our mass is there. It's not any one point is there where, but what we are considering at our belly button, that is the centroid of the human being. So their mass is acting, or just like in UDL. Okay, this is uniformly distributed load. That what we are assuming at the midpoint of this whole, whatever the magnitude of this is there, that is acting. So same way here, this also we assume that acting at the centroid, and that centroid from here it's a very less. So that what plans, that area of concentration area also will be of that one, known as boom. So we could therefore replace a stringer and a spar flanges by concentration of area, right? So now instead of a stringer and a spar, we have the concentration of area known as what? Booms. So that is given, called as boom, over which the direct stress is constant, because already we had seen direct stress is constant because of the small in size is constant, and which are located along the midline of the skin. So where it's located? Here, just the midline. Everywhere you can see, this one, right? So it's a midline of the skin. So you can see here, half portion is above the line and half portion below this line. This line is only the skin. Thus it's a midpoint of that one. Over which, okay, midline of the skin as shown in figure 2 here. So now this is the idealized of the figure 1, right? Figure 2 idealization of a wing section. Okay. Now, shear stress distribution that continues is the in wing and fuselage section of the type shown in figure 1, the stringers and spar flanges carry most of the direct stresses. So just see here, this remember, the stringer and spars carrying the most of the direct stress, while the skin is mainly effective in resisting shear stress. So what we are doing, so here direct stress, that fluid is acting like this, but over the skin what happened, that whatever the load is acting along the skin, only it's acting. That's why that is called the shear one. So skin is what? Experiencing shear stress, and stringer and spars that experiencing or carrying direct stress. So while the skin is mainly effective in resisting shear stress. So what skin is doing? It's resisting the shear stresses. Although it also carries some of the direct stress. That direct stress, why? Because that skin is supported by the stringer and spar, and stringer and spar, it's so this is there, right? So now this is the direct stress on a stringer. Now if a skin will be here over this one, that is in contact with the stringer, then what happens? This direct load will also act on the skin. So that's why that is there. But mostly it's for shear stress. The direct stress carrying capacity of the skin may be allowed for by increasing each boom area by an area equivalent to the direct stress carrying. So direct stress carrying capacity of the adjacent skin panel. So for adjacent skin panel, how much they have the capacity to hold the direct stress. Okay, that much, according to that only we can change, or we can add, or that we can increase or decrease boom area. Okay, by an area equivalent to what? That is direct stress carrying capacity. The calculation of these equivalent area will generally depends on initial assumptions. So what we assumed initially, that calculation of that equivalent area will depends on what? Initial assumptions as to the form of distribution of direct stress in a boom skin panel. So whatever the initial assumptions are there, according to that only this equivalent area will be there. Okay, now idealization. So this one is important. Same just like earlier what we had seen for this one. So idealization of a closed panel of open section, right? Suppose that we wish to idealize the panel of figure 3A. 3A, right? So now this is required to panelize, right? Sorry, idealize, not panelized. Okay, idealize the panel figure A into a combination of direct stress carrying boom and shear stress only carrying a skin. So here in this time, the skin is carrying only shear stress, and booms are carrying, that boom stringer and spars are carrying the direct stress as shown in figure 3B. So just see here. So now this is the boom. After this, whatever the equivalent area is there, this whole area, now that converted to boom area, right? So that we have to find how much boom area will be there. That means for this side, what will be the value of B1, what will be the value of B2, right? That we have to find. So now what we are focusing, that all stresses acting on the boom only. So now here this is sigma 1 along B1 and sigma 2 along B2. So now after booming, here assumptions is what, there is no shear stress, that direct stress over this side. So in this case, TD is equals to T having some thickness. But here after idealizing, that TD will be equals to 0. Okay. So now let's see. In figure 3, the direct stress carrying thickness TD of the skin is equal to its actual thickness T. While in figure 3b, TD equals to 0. So after idealizing, that TD carrying direct stress becomes 0. Suppose also that the direct stress distribution in the actual panel varies linearly from an unknown value sigma 1 to unknown value sigma 2. So now let's see here, sigma 1 to sigma 2, it's a varying, right? So in between some, that sigma 1 to sigma 2, it's just varying. Okay, clearly the analysis should predict the extremes of sigma 1 and sigma 2, although distribution of direct stress is obviously lost. So now here what will be there, what sigma 1 and sigma 2 will be there, but direct stress is obviously lost, means direct stress won't be there. Since the loading produced, the direct stresses in actual and idealized panel must be the same in both the cases. That ideal, okay, that direct stress should be same. We can equate moment to obtain expression for the boom area. So now just take the momentum of both and then equate to get the B1 and B2, that boom area. So B1 is the boom area of first boom, B2 is the second, that area of second boom. Thus taking moment out the right hand edge of each panel, right? So just take moment about this right hand of this panel and just equate it, right? So for sigma 2, so just see sigma 2, okay, that is what, just area, taking moment is force into perpendicular distance. So sigma force is what, sigma into area. So here sigma into thickness is TD into where it will act at d by 2. So this is, okay, sorry, TB, not D. TB will be the area, thickness into width, right? This one, that will be the area into where it will act at somewhere center of this one, okay? So that into B by 2. So F will be equals to that sigma A. So sigma T dV is F into perpendicular distance, right? So moment will be equals to F into D, right? So D is here B by 2. So F is sigma TD into B into B by 2. So sigma 2 TD B square B by 2. TD B square by 2. So this will be the moment for first side. Similarly, for this one also, again you can see sigma 1 minus sigma 2, whatever the difference will be there, because both are not same. In this figure you can see, yeah, the difference is there. So whatever the difference is there for the actual one, right, that difference into TD into B2 by 3. So let's see how you will find this one, because difference is there and that we have to find. So first take this one, okay, this is there. So now this is rectangle, so you can see this as uniformly load, and for rectangle we just found, okay. So where it is acting, that at center of that centroid, that is at B by 2. Now what about this one, right? This also is there after drawing, so this is there, right? So now this is forming a triangle, right? So this is forming a triangle. So now for triangle we have to find, so where center of gravity is acting, right? From this side it's a 1/3, from this side, so say around sigma 1 we are finding, so it's at 2/3 of that one. So now sigma 1 minus sigma 2, the resultant of this will be there, because what, this is sigma 1 minus sigma 2, because this is sigma 1, this is sigma 2, the difference will be sigma 1 minus sigma 2, this one. So sigma 1 minus sigma 2 into TD into B, that will be the area where it will act at 2/3 of B. That is equals to what, this one, sigma 1, or from this side sigma 1 B1 B. Okay, so that is for the first equation from this side. Now take the equation moment from this side. Okay, so now after solving, what you will get? So let's solve. Okay, so just expand this one. So now what we will get? Sigma 2 TD into BA square by 2 plus after this one. So sigma 1 into plus sigma 1 into TD. I'm just multiplying with this and opening the bracket. So sigma 1 into TD into B into 2 by 3B and this by 2. Then minus sigma 2. Okay. Then sigma 2 TDB into 2 by 3B, right? B into TDB into B 2 by 3. So this side, that will be equals to this one. So that is equals to sigma 1 B1 into B. So now just see here. This sigma 2, what cancelled? Now what is left? Sigma 1 TD into B into B in 2 by 3. Okay, this divided by 2 equals to sigma 1 B1 into B. So now we can cancel 1B, 1B. So now what we have? TD into B. So just writing TD into B. Okay, this 2 and this 2 will come here. So 6. Okay, so 6. And then after this, it will be just after taking common these two terms, this will get T2 plus sigma 2 by sigma 1. Okay, so this will be for what? That B1 value. Similarly, take moment along B2, then sorry B1. So this is moment along B2. This is moment after same equation, moment along B1, then we will get the value of B2. Similar value, just see here how you will remember. If B1 is there, then sigma 2 will be in the numerator. 2 plus sigma 1 by sigma 1. Here B2 is there, means just opposite, that sigma 1 will be in numerator and sigma 2 will be in denominator. Okay, so now we have the boom area B1 and B2, what we are. So like B1, B2, here only 2 booms are there, so 2 area. If more booms, like 5 booms, then B1, B2, B3, B4, B5, like that, depending upon how many booms are there, right? Based on that, you have to find the boom area. Now, suppose that an open or closed section beam is subjected to given bending or shear load and that the required idealization has been completed. So after that, what? For open or any closed beam is subjected to given bending or shear, whatever is there, then that after that required idealization has been completed. So whatever the requirement of idealization is there, that is completed means after idealizing. So after idealizing from this to this, now what will be the next step to solve? So this one, the analysis of such section usually involves the determination of the neutral axis position. So what is that? First, determine that with that you can determine the neutral axis position and the calculation of sectional properties. After deciding the neutral axis, find the calculation of what? Sectional property. Sectional property when we saw just moment of inertia, just like I-axis, I-Y-Y, right? Along which axis you are taking the moment of inertia, in that moment of inertia you have to find first. The position of the neutral axis is derived from the condition that the resultant load on the beam cross section is 0. Then only that will be the what? Neutral axis. So where the resultant force will be 0, that will be the neutral axis. Okay. So for that, whatever the sigma z into A. So sigma A into A is area, sorry, force. So force, this for overall A. That's why here this, that along this z is there. So sigma z dA is equals to 0. Means the total force acting at that particular point should be equals to 0 for finding the neutral axis. The area A in this expression is clearly the direct stress carrying area. So whatever area you will take, that having only the direct stress carrying, that is a stringer or a spark, because that only we are converting into the booms. It follows that the centroid of the cross section is the centroid of the direct stress carrying area. So whatever the centroid will be there, that will be also the centroid of the direct stress carrying area, depending on the degree and method of idealization, how you are idealizing. Okay, based on that, that cross section stress carrying area will be there. The sectional property, let's see, Ixx and so on, Ixx, Iyy, okay, and so on must also refer to the direct stress carrying area. So whatever in case of sectional property, that Ixx and Iyy moment of inertia along x axis, Iyy moment of inertia along y axis, that also will experience the direct stress only. Okay, now you can see the direct stress carrying area. Now bending of open section beam. So in direct stress distribution, the coordinates x, y of points in the cross section are referred to axes having their origin at the centroid. So now what we are doing here, we are considering that origin at the centroid of the direct stress carrying area. So whatever the stringer parts or that boom area is there, which carrying direct stress, right? Their origins are at their centroid. Furthermore, the section properties here, Ixx, Iyy, Ixy, are calculated for the direct stress area only, right? So these property will carry that calculated for having or experiencing direct stress carrying area only. In the case where the beam cross section has been completely idealized into direct stress carrying boom and shear stress only carrying panel. So shear stress carrying only panel and direct stress carrying boom, right? Means now both are separated. So boom is carrying only the direct stress and the skin is carrying only the shear stress. The direct stress distribution consists of a series of direct stresses concentrated at the centroid of the boom, right? So whatever the direct stress distribution will be there, that we are just, because its size is very small already, we assume for stringer in spar. So what we are considering, the direct stress is concentrated also at the centroid of the boom. Okay, so let's see once we are again. So what is there till date we had seen, that is the for the general cross section was there, just simple. Now if complicated is there, then what happened, how to solve? So means for complicated structure, what we will do, we will take some assumptions, right? With that assumptions, but that assumption should not affect that much the property. For that, what we have to do, the proper that after with that assumptions, accuracy also should be maintained. So as much as possible, we can achieve the accuracy. For that, what we are doing, we are just replacing the area or near to that area. Why? Because the stringers and spars are very small. So the center of gravity, that's CG of that one, or centroid of the stringers and spar, just assumed as that also is very small and that is very near to the skin. And hence, what we are changing the boom, that for those stringers and spar, and that also their center must lie at the skin. Okay, that's in the center. Means that skin should pass through the center. Okay, so now whatever the complex is there, in that what we have to do, okay, that stringer spars or boom will carry only the direct stress, and this one skin will carry the shear stress. So now the thing we have to remember is what we have to idealize in such a way that should be as much as accurate to the original will be there. Okay, that means that should not get affected that much. Okay, so now you see, so after idealizing, what happened, this direct stress carrying, okay, that TD becomes equals to 0. That is given in the next figure. So just here, so this is the original one, this is the idealized one. So in this sigma 1 to sigma 2, it's a varying. So first what we will find after taking moment along any one, this will be this is a rectangle. So for rectangular, here is the moment for rectangular load, this one. Now this is the triangle. So for rectangle, where it's acting at b by 2. So that's why we multiplied b by 2. So sigma 2 is the stress area TD into b by 2 will be the, sorry, b will be the area, right? Area of rectangle. So this is b and this is TD. So TD and b will be the area, and b by 2 where it's acting, that perpendicular distance. So that is the moment from this side, that rectangle. Now we have to find what moment of this triangle. So what will be this one? Sigma 1 minus sigma 2 into TD into B, and this 2 by 3 where it's acting from this side, because center of gravity, that's easy, or centroid of the triangle is 1/3 from this side or 2/3 from this side. So here, from here we have taken, so this 2/3 of this one. Okay, that is equals to what? This sigma 1 B1 B. Now just expand and simplify, you will get what? B1 equals to this one. Similarly, you can take moment from this side, then another equation will be there in terms of B2, right? Then you will get the value of B2 like this. So just see here what you have to remember. In this things everything will be same, only for B1 sigma 2 will be in the numerator and sigma 1 will be in the denominator. So whatever you are finding, that should be in numerator. Here you are B2 finding, this B2 should be, that sigma 2 should be in numerator. Okay. So now after idealization, what happened? The total force or resultant force acting at the what? That point where that point is only the neutral axis. So there that total resultant force must be equals to 0. So over this entire span, sigma z into dA, that should be equals to 0. Means what? So that cross section or centroid of the direct stress carrying area will be that one, and degree and method of idealization. Then the sectional property Ixx and so on must also refer to the direct stress. So now whatever is there, once we change to the boom, then we will consider the direct stress area only when we will find the sectional property also. Okay, so what are the sectional property? That will be Ixx, Iyy and Ixy. Means along x-axis axis you have to take the moment of inertia. In this case along y axis means here, right? So this is x, or you can say minus x. This is y minus y. So along this axis, that is Ixx, along this axis, that is Iyy. Now anywhere like this along, so this will be the Ixy. Okay, so that's why it's called as sectional property along which you are taking the moment of inertia. Okay, so this is the reference, means you can refer to the TSG Maxian force addition. Okay, so related to this, if you have any doubt, you just comment here, or you can just contact me for your doubts. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.